In the last video, we established a few different characterizations of when a vector field is conservative. So one of those was its integral over any loop is 0. And the other was that it arises as the gradient of some other function that we called a potential function. But really the one is sort of more useful in this direction. Like if you know f is conservative, then you have this property that its integral over any loop is 0. It's hard to apply this in the other direction because then you would have to calculate an integral for every possible loop. So that's not really feasible. So we want to know how, like, being conservative is a very useful property, but how do we actually check it? So we can get more mileage out of this characterization. So suppose that f is equal to mi plus nj plus pk, where m, like all of these are functions of x, y, and z. I've just omitted that. Then if this is df, so this is del f by del xi plus del f by del yj plus del f plus by del zk. Well, then by symmetry of mixed partials, we'll have del m by del y. This is del squared f by del y del x. But that we've seen is equal to del squared f by del x del y. So this, and then that is equal to del n by del x. Similarly, I'll erase this. So similarly, we'll have del n by del z is del squared f by del z del y, which is del squared f by del y del z, and that is del p by del y. And then finally we'll have del m by del z is del squared f by del z del x is del squared f by del x del z, and that's del p by del x. So each of the components of f is appearing in two of these equations. So like n, m, and p, and so we take the derivative of, like, the partial of each component with all of the variables. So like p corresponds to z, so we take the partial of p with respect to y and x, and then compare that to, like, m corresponds to x. So we compare these two, and so these have to be equal. So a necessary condition for so if f is equal to del f, or maybe I should say, since so if f is conservative, then these three equations have to hold. And so this gives like we can just calculate some derivatives, and this will give a first check to see if something's conservative. So let me make a remark. So actually, I want to move these over here, so I'll just rewrite these. So del n by del z has to be del p by del y, del m by del z. This has to be del p by del x, and this has to be del n by del x. So I'm going to abuse notation a little bit and write del equals del by del xi plus del by del yj plus del by del zk. And then, if I had like a function f then this would be our definition of the gradient of f, which is sort of why we're doing this, but I'm going to just write this without any f attached to it. So we're going to consider the cross product of this sort of vector so nabla, so I shouldn't have written an arrow over nabla. So if we take nabla cross f, so that'll be determinant I, j, k, del by del x, del by del y, del by del z, m, and p. So this is del p by del y minus del n by del z I. So now notice here we've got sort of the p and n correspond to z and y, and then y and z. So we have the variables and the components not corresponding to x, which is sort of what I corresponds to. And then j, so this will be del m by del z minus del p by del x plus, okay, so this is del n by del x minus del m by del y. Okay, so this cross product, this is called the curl of f. And we'll study this more in the coming sections. So what these equations show is, so here this delta, or yeah, del n by del z has to equal del p by del y. So that would be saying that this is 0. Similarly, this these two being equal means that this component is 0, and these two being equal shows that this component is 0. So another way of stating this is that, of stating our characterization, is that if f, or our test I should say, f is conservative, then the curl of f is 0. And so this is what I mean when I say the component test. So for example, if we take f equals x, y, I plus x, z, j plus y, z, k, del by del y of xy. So we'll take this. This is equal to x. And then we also want to take del by del x of the y component, xz. So that's z. But these are not equal to each other. So f cannot be conservative. Okay, so this is a necessary condition but it's not always sufficient, meaning there can be a vector field can have curl equal to 0 without being conservative. And in fact, this turns out to depend really depend on the domain D that we're considering. So if our vector field is defined everywhere, then it'll turn out that it is sufficient. Any conservative vector field, any vector field with curl equals 0 is conservative if it's defined everywhere. But otherwise, we can have things which are conservative but not, which have curl 0 but are not conservative. So here is an example. So we'll let f be 1 over x squared plus y squared negative yi plus xj. So again, this is a form of an angular vector field. But we should contrast it to, so this angular vector field is not defined at the origin. If we took negative yi plus xj, but didn't divide by 1 over x squared plus y squared, then del by del x del by del y of negative y is negative 1, del by del x of x is 1. So this version of the angular vector field is not conservative. But I claim that this one is. So, it's not, this one's not conservative, but it'll satisfy this condition. So let's calculate. We don't need to calculate the full curl. If I calculate del by del y of negative y over x squared plus y squared, this is, so you have to use quotient rule. So that's negative x squared plus y squared, derivative of the top times the bottom, and then minus, so then plus, and then derivative, so 2 y squared. This is all over x squared plus y squared squared, and del by del x of x over x squared plus y squared. This again will be something over x squared plus y squared squared. So we take the derivative of the top, x squared, so that's 1, and then times the bottom, x squared plus y squared, and then minus this, so minus 2x squared. And so this becomes, the top here is y squared minus x squared. And also here we get y squared minus x squared all over x squared plus y squared squared. So this does satisfy the component test. However, I claim that this is not conservative. So this one we can see is not conservative. It doesn't even satisfy the component test. But this other one is still not conservative, even though it satisfies the component test. So what we'll do is we'll integrate this over a loop and see that we get a non-zero result. So let's just integrate over the standard, the unit circle. So C, parameterization cos Ti plus sine Tj for t between 0 and 2 pi. So this is r of t equals, so now f of r is 1 over cos squared plus sine squared, so that's just 1. So this will be negative sine ti plus cos tj, and dr will be also negative sine ti plus cos tj. So if we take an integral, integrate this, integral cf dot dr is integral 0 to pi of this, oh sorry, that was supposed to have a dt at the end, dot this dt, and so then this is sine squared and cos squared, so this is integral 0 to pi dt is 2 pi. So f, despite passing the component test, is not conservative. Okay, so we have to be careful. So as I said, this is related to the fact that f is not defined at the origin. And in some very vague sense, this is, in some very vague sense, the only thing that can go wrong. So the circle example, in some sense, encapsulates all the examples. So in the following sense, we say that so we say our region D is simply connected if every loop in D can be contracted to a point. So for example, Rn is simply connected, but R2 minus the origin is not. Although Rn minus the origin is for n greater than equal to 3. On the other hand, R3 minus the z-axis this is not simply connected. So here, if you have a circle, here's sort of the missing origin. We have a loop like this. There's no way to contract it without sort of getting stuck on the missing point. Some other examples are a sphere is simply connected, but a torus is not. So on a torus, loops that go sort of two different types of loops that can go around the entire torus, which can't be contracted to a point. I'll say a lot of sources require any simply connected thing to also be connected, but the textbook doesn't. Okay, and so then what I meant by a circle is this is sort of a circle. A circle being the only thing that can go wrong is that theorem, if D is open and simply connected, then any vector field F on D for which the curl is 0 is conservative. So in this case, for these types of domains, we can just check that criterion and then conclude that it's conservative. Maybe I should say, assume that we'll assume that the components of F have continuous first partial derivatives, which of course will always be satisfied in practice.